Okay, as an introduction to the binary system, we're going to do a way of representing characters on the screen or for printing. A lot of computers use slightly different systems to what I'm showing, but many dot matrix printers or printers capable of creating images by firing pins use this system for actually creating the characters, which is why it's so widely used. What we need to be able to do is work between the binary system, which is based on zeros and ones, and the decimal system, and you need to be able to encode and decode to create these symbols. So what I'm going to go through is how you can create, for printing, characters like these. We'll do possibly some of the BOM and maybe look at some values for these going through. There's space there for you to make some more of your own as well. So, why the binary system? Well, when you think of a computer, what do you think of? Most people, when they think of it, think of a piece of plastic or metal with a keyboard, a screen. These sort of computers have only been around since the 1970s. Before that, they tended to be fairly large boxes or even whole rooms. Some of the earliest forms of computers were the Antikythera mechanism, which is around 100 years before the Common Era. It's a navigation tool, and it did some very complex calculations to help people know where they were at sea. Then mathematicians started using it. So 1822, one of the most famous computing devices made was Charles Babbage's, I missed out an A there, sorry, his difference engine. This was used for calculating logarithm tables and big systems. He never built the full machine. He built a small version to show that it worked. But if you look at that, the amount of brass and metal involved in there to be finely engineered, it would have cost the equivalent of millions and millions of dollars at that time. So he managed to build the concept, get it to work, but it didn't go on further. Then the next step was I started going from mechanical systems that worked on base 10 to systems that combined electronics and things. And the ENIAC system used by the US Department of Defense was still a decimal-based computer. It worked on digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in columns of 10. And one of the problems they found in the process was finding that the differences in voltages needed had to be finely controlled. So as they started moving from mechanical means to more electronic by thermionic valves, they were having more and more errors because the different, if you said that the number range was equivalent of 100 volts, I think at that time that's a sort of fairly sort of similar to the sort of voltages they were using. If you every 10 volt was a digit, and that takes a lot of power, a lot of heat, means the system can easily overheat and create wrong digits. Not only in Britain, but the Polish bomber and other devices used for decoding secrets started relying on using binary systems because it's a lot easier to control the difference between two voltages. And you can run it at a lower voltage, which means less power, means less heat, and it means the system could actually be a lot more accurate. One downside for using binary is the circuitry. If you take a circuit that's designed to work at base 10, you need about 3 to 4 times as many components to be able to represent the same system using binary. But the payoff is we were able to manufacture that from thermionic valves to create transistors, from transistors to create integrated circuits, so that we've now got millions and millions of these little tiny switches and bits of memory saying on or off, down into a chip that allows things like our modern laptops to work. So let's go through an example of decoding a binary number. At the top we've got our normal decimal system or denary system. And this represents the number 3,207. And as you would have found in primary school, the 3 represents 3,000s, 2 represents 200s, 0 is 10, and 7 is 1. Now, if you're only going to consider things as being on or off, what happens is you consider one column and you can say it's either on or off, so it's either white or black, and I'm saying white is off. So if I want to count, I can go 0 and I can go 1. When I want 2, I haven't got enough information, so I need a new column. So 2 is the label for the next column. So I've got 2 and 0 is 2. I can then do 2 and the 1 column. That gives me 3. I've now run out of digits, so I need an extra column. I now need a 4 column. And as I keep going through, I need, from the 4s column, I need 4s. I can then do 5, 6, 7 fills it up. And so I can create the next number, I did a new column, the 8s. And what you'll recognise is the numbers at the top are doubling all the way through. That's what the base 2 system means. Denary multiplied by 10, decimal multiplied by binary multiplied by 2. So it's 1, 2, 4, 8, 16, 32, 64, 128. And what you can see here is a build-up of a picture. And that's how we can, the digits 0, 1, 2, 3, 4, 5, 6, 7 can build this picture. And that's how you can create the characters that I showed you before. You choose the right numbers and the certain lights turn on and you can now work on them. So let's take the digit here for 6. We've got 0, 0, 0, 0, 0, 1, 1, 0. And the 2 ones are in the 4 and the 2. If we add 4 and 2, we get 6. Fairly straightforward. A few more examples here. This top one here, what we have is we have the 16 and the 8 turned on, so that's a total of 24. Next one down, we've got 32, 8 and 2. Add those together and you get a total of 42. Some of these are other common patterns that people use in them, work the numbers through. The interesting thing to notice though is if I want to fill up everything up to 128, I turn all the other bits on. Well, the reason for creating the 128 column is we want one number bigger than this. So this number, all of these, must be, all of these, 64, 32, 16, 8, 4, 2 and 1, must be one number less than that one. So it's 127. It's one of the ways people create patterns quite quickly. 255, well, the next number we need is 256. So filling up all 8 bits is 255. To go the other way, we've got to do equivalently of trying to divide by powers of 10, or in this case, powers of 2. So we start as far to the left as we can and think, can I divide 137 by 128? And the answer is yes. By a quirk of the way that binary works though, division is very much more closely allied to subtraction than it is with decimal. So we don't have to do the multiplication, we can do a subtraction. Can we take 128 from 137? Yes. That gives me 1 with 9 remainder. So 137 minus 128 is 1, remainder 9. What have I got left to split up is the 9. So we've already dealt with 128, so we store it. So we go through again, take the 9, carry it forward into the 64. Can we break that by 64? And I'm doing this by subtraction. You can think of it as division as well. How many times does 64 go into 9? None, remainder 9. Or can I take 64 away from 9? No. Then I've got 9 left over still. That's why the division and subtraction are the same, or very much similar. We're not having to say how many 64s are there in 9. We just have to know, is it or is it not? And the binary system is only yes or no. So let's go through. 9 is minus 32, no. So we've got 9 left over. 16, 9 minus 16, no, we've got 9 left over. 9 minus 8, yes we can. So we've got a 1 in that column. And we've got 1 left over to be subtracted. So 1 minus 4, no. So we keep carrying forward the remainder. And we keep going until we get down to, have we got a 1 left? 1 minus 1, yes, with nothing left over. So we've now actually split out and dealt with all the parts of 137, and the bits we've actually needed are the 128, the 8, and the 1. So it's written as 1, 0, 0, 0, 1, 0, 0, 1. Each one on here is the digit. Let's look at the next one. It flips through, so 100 minus 128, can't do it, 100 left over. 64 minus 100 minus 64. Yes, we've got 36 left over. 36 minus 32, the next column. Yes, so remainder 4. 16, no, we can't take 16 from 4, so we've still got 4. 8 from 4, no, so we've still got 4. 4 from 4, yes, and we've got nothing left over. 2 from 0, no. 1 from 0, no. But we still need to make sure these places are correct. And I've put one too many zeros in this one. I've got, yeah, this last place, there's one too many. We should have been counting these zeros. So it's 0, 1, 1, 0, 0, 1, 0, 0. There's an extra 0 on the end of that slide. So you've got an exercise in this sheet. And what we can do is you can play about with these grids and type numbers in at the top. So let's see if I can turn on 8 and 1. Well, 8 and 1 is 9. Put it on, and it colours it in for me. If I type 128 and 32, that's 160. So I can add the numbers together. We did 42 before, that's 32, 8, and 2. That's 42. Hang on, there's those ones turned on. Okay. So you've got a number of challenges. The ones with purple, you need to try and come up with the number to only cover the purple bits, not the extra white. So in this one, I've got 2, I've got 4, I've got 8. That's 14. 2, 4, and 8 gives me 14. Here I've got 16 and 1, that's 17. So you need to remember what these numbers are, and you can go in and type them in for yourself on your, you can go up to the top and highlight them to help you work through. And I'll probably leave that unlocked for you. You've got all these characters to do. So we'll clean this out. So write the numbers in the blue bits. Then the next one, you've got to decode these numbers. So you've got to say which values are on. So if we put a 1 into the box, it will colour it for me. So what's the number at the top here? Those numbers I need to fill in for myself. 1, 2, 4, 8, 16, 32, 64, 128. So 60. No, don't need 128. Don't need 60. 32 I do. And there's 28 left. 28 minus 16, yes. 12 left. 12 minus 8, yes. 4 left over. 4, yes. Nothing else needed. And if you fill those in, you should get a recognisable character. There's 2 of them there for you to produce. You just type in the number 1 to make it go. I think you can do any character actually. Yeah, any character will make it work. Okay, describe what you get. And then you've got 4 examples here that you can go on to, and you can make Christmas decorations or the Cyrillic alphabet. You may notice that Cyrillic alphabet is often missing from computers. Okay, so that's how the exercise you will be using. Finally, most games were created using multiple colours. And to create the multiple colours, each colour on this system would need to have its own character definition. So these little 8x8 sprites, which we used for on printing and others, with colour displays, they become a bit of an issue. So other ways have been encoded to create these sorts of characters or sprites, moving characters on the screen. But to create things like Mario, I'd need a character representing the white bit, a character that represents the red bit, character for his skin, brown bits. Each bit character would need its own definition. And that's why other systems have been used. I'll leave you with the last thing. It is a joke. There are 10 types of people, those that understand binary and those who don't. Put into the comments how this is funny, what makes it funny, why does it work. Okay, there you are, that's your lesson, guys. Try and get these characters, these shapes displayed and make up for yourself. Try and do some Christmas tree decorations or something. It is only black and white, but try.